Hello and welcome to discussion on reaction mechanisms, um, catalysts, and some other little pieces of kinetics we need to discuss before we complete the topic. So, let's talk about the fundamentals of reaction mechanisms. Reaction mechanisms diagram the series of steps in which a reaction occurs. We've already looked at the fact that reactions aren't usually simply one simple reaction. It's often several other reactions taking place in concert to make a reaction take place. Um, Terminology we're going to use, we'll sometimes talk about reaction intermediates. We've already kind of started using this word. Or intermediates are neither products nor reactants in a balanced equation, and they will be used in subsequent steps in the reaction. And in the overall reaction, you won't see them at all. But they were there at some point during the formation of the products. So the elementary step is a reaction whose rate law can be written from its molecularity. And so this shouldn't be too confusing. We'll see an example in a minute. But basically what it means is the coefficients of the balanced equation are what the reaction is the simplest way to say it. So molecularity, what that means is the number of species that must collide to produce the reaction represented by the elementary step. So it's basically in that basic fundamental mole ratio of a reaction. So this is an example of a reaction that takes place in multiple steps, where the overall reaction begins with hydrogen and iodine monochloride, ending with iodine gas and hydrochloric acid. So what we see happen, though, is we see an energy required to build the uh, activated complex that then results in making an intermediate set of products, which then must be activated again and then form your final set of products. Where what you should notice that you have at some point in here hydroiodic acid that's completely an intermediate. It's not part of the products or reactants. But this is a multi-step taking place where there's an overall energy release from beginning to end and potential energy. Some fundamentals of reaction mechanics. We'll talk about reactions in terms of unimolecular steps, where the reaction step is involving only one molecule, and this is usually what we're going to see in a first order reaction, literally one thing. So look at the diagram down here, one particle resulting in making products. A bimolecular step is a reaction step involving the collision of two molecules, and that's what you'd see in a second order reaction, where you have two different things involved. And then we have beyond. So looking at the definitions of unimolecular, bimolecular step, we see what we have colliding in order to produce a product in each molecularity. One if there's one, two if there's two, and then so on. This is a graphic just to illustrate the concept. Coming next is the rate determining step. In any series of reactions, the rate determining step is going to dictate the rate of the reaction. So we have in these three images a small funnel with two larger funnels. And regardless of how you pour, you're going to have a log jam at the smallest funnel. And that's the concept behind the rate determining step, the slow step of a reaction driving the kinetics involved. So if we look at this three-step reaction where we see A plus B plus C making ABC in two different steps, we have A plus B making AB. That's our slow step. That's large activation energy, slow step. And then the second reaction with a smaller activation energy, the faster step. This reaction, the one in red, slow, is going to be the reaction we measure for kinetics. We will ignore this in terms of how fast this reaction goes because this reaction is much slower, therefore dictates the rate of the reaction overall. So this kind of goes back to what we were talking about a minute ago as far as unimolecular, bimolecular, termolecular, where you can see, given the various rate laws, expressed here, how that impacts what your reaction would look like on the elementary reaction over on the left. So when we write our overall reaction mechanism, it must add up to the overall balanced equation and agree with the rate law. The trick is we can't prove a mechanism absolutely. We can only come up with possible mechanisms. So this is pretty much theoretical in nature, but it works out mathematically and agrees with the overall reaction, then everything should be in order. So here is an elementary reaction. We have nitrogen monoxide, nitrogen dioxide making dinitrogen monoxide making nitrogen monoxide and nitrogen gas. What we're looking at here is how we would write our rate law, and that's that. In this reaction below, we have this reaction taking place. 2 moles of nitrogen dioxide and fluorine making this compound is thought to proceed by this reaction rate, or this rate law. And so we have this expressed rate law. We are going only after the kinetics in the slow step. Okay? So an elementary reaction is just going to be what your reactants are. When we look at a reaction mechanism, we only pay attention to the reactants in the slow step. Somehow it went past. When an intermediate in a reactant, in our overall reaction is a reactant in the rate determining step, the derivation of the rate law is more challenging. So we'll have to rewrite a little bit of our rate law in order to determine what our rate law will be. The reason is, if you look at our desired reaction here, our slow step contains nitrogen trioxide and carbon monoxide. Carbon monoxide is part of our original reaction, but nitrogen trioxide is not. It's going to be considered an intermediate because it's not present in the overall reaction. So our rate law can't contain nitrate as it does here in purple. So what we would do is, using these two reactions, build an equation that allows us to solve for something that's equal to the nitrogen trioxide. And so what we do is we can express each one of these as a rate law on its own, this mechanism here, NO2, NO2, and use the rate law for that, and then do the same thing for the product side of this reaction also. So because they have the same K, we can just set them equal to each other. So what we do is we do that. We write a mechanism for each with the set equal to K, which allows us to cancel K and then solve for nitrogen trioxide, which gives us this expression here, nitrogen dioxide to the power of 2 divided by nitrogen monoxide. We simply take that original rate law, we have nitrogen trioxide in purple, and replace this piece that we determined was equal to it into the rate law. Therefore, we get this new expression for rate law here that does have a denominator. That's okay. It is okay to have a denominator. What we don't want to do is build a rate law based solely on reactants and products. We know that our slow step rate law is still true because we know that nitrogen trioxide, we found something equal to that with items that are in the original rate law, or that are in the original reaction mechanism. In this reaction, we have 3 different steps in between, with 1 slow step here. Chlorine and this setup for slow. We have our overall reaction up top. Here's our rate law. Since we can go ahead and go to our slow step and write our rate law based on our slow step, chlorine is considered an intermediate, so we have to find something where we know it's equal. We find it in this reaction up top, something we can solve for, where K is the same on either side of the reaction. So what we do is simply solve for the Cl, which gives us a half power of chlorine gas, which is part of our original reaction, and allows us to replace this chlorine intermediate with the chlorine gas to the power of 1/2, or 0.5. Either one of those is acceptable. So basically what we're doing is we're adapting our rate law to reflect things that are in the goal reaction. So some of the big ideas about kinetics is we have to understand that in the chemical system, in order for a reaction to take place, particles must collide with proper orientation, and they must collide at proper speed. And we know that in any sample of any chemical compound, and the model is usually done with gases, that particles are moving at all sorts of speeds. And some of those particles are moving at speed sufficient to create a reaction, some aren't, and that's okay. So we understand that if we increase temperature of a system, usually we're going to increase the possibility of having a reaction. Rate and rate constants often double for every about 10 degrees increase in temperature. And this is a rule of thumb you're going to want to have on the AP test. So they'll often present you a scenario in which temperatures increase a little bit, And we need to kind of look back and say, well, what's that going to do to my rate? My rate constant, you need to know that it should double for about every 10 degrees Celsius. This will come back, okay? So make sure you take special note of that sentence. Activation energy is the energy that must be overcome to produce a chemical reaction, and this is really what's slowing down our reactions, is the significant contribution required to activate a reaction. And when we look at activation energy, in this plot here, we have this blue line at temperature 1, and then we have temperature, oh sorry, this is not what I'm looking at. This is Boltzmann diagram. Let's go back up to bullet number 1. This Boltzmann diagram is collisions and energy. So they look a lot alike, don't they? When you're looking at a Boltzmann diagram, we already know that we're looking at various numbers of particles at different speeds at different temperatures. So temperature 1 is a lower temperature, temperature 2 is a higher temperature. And you can see that in this graphic, at temperature 2, we have many more particles that are able to reach activation energy than under temperature 1. Okay, and the difference under the area of the curve, hello calculus, tells us the number of particles more we are able to activate at temperature 1 rather over temperature 2. So keep this in the back of your mind that Boltzmann diagrams are also going to be a potential discussion in kinetics. So this is back to a sort of a rudimentary idea. Rate reaction depends on activation energy, not change in energy. Now delta E is, we'll refer back to it as delta H. So the delta E here is the same thing as enthalpy that we learned earlier on thermo, but for now it's listed as delta E in the text. We're going to stick with that. The higher the activation energy, the slower the reaction is at a given temperature. Molecules and collisions have varying energies. As temperatures increase, more collisions will have sufficient energy to overcome activation energy. And here it is again, as temperature doubles, the fraction of effective collisions increases exponentially. So we need to keep that rule of thumb that 10 degrees Celsius roughly doubles activation energy. This statement's backwards, and it's saying as you double temperature. So we're talking about as a 10 degree temperature increase roughly doubles rates of reaction. So this is more of a graphical image of what I want you to know about why reactions actually take place and what's required when particles collide, individual molecules or atoms collide. We have to have, first of all, proper orientation. So this is just a particular model of this compound. And we see that if the particles collide on end, we get a nice reaction where bromine and nitrogen monoxide form. If they collide head-on, we get a similar reaction. If they collide tail to tail, nothing happens. So the actual orientation of particles in space can dictate whether or not a reaction happens. So we need two things in order for a reaction to occur, not just activation energy. They have to be moving at a certain speed, but they also have to hit at a proper orientation. So these two different things both contribute to whether or not a reaction takes place. And this is even with adequate speed, if particles hit tail to tail, you're not going to get a reaction. So now I want to talk about the ARRHENIUS equation. The ARRHENIUS equation allows us to calculate activation energy and look at activation energy under different conditions. Now, it's not an AP topic. That doesn't mean it's not important. So what we're going to do is kind of investigate a little bit and introduce a few ways we can be questioned and leave it at that. As activation energy increases in a reaction, the K decreases, and that should stand to reason. The larger the activation energy, the slower the rate of reaction, and so K is going to be going down. The ARRHENIUS equation describes a line. We can plot the inverse of time versus the natural log of our rate constant and get a straight line whose slope is negative activation energy divided by the universal gas constant, R. So here is that line. We have the natural log of our rate constant. We have the inverse of, temperature. We have the inverse of temperature in Kelvin because we're dealing with energy again. I apologize, it's a big T. Where slope is equal to our change in the natural log of rate constant divided by the change in the inverse of temperature. And we should note, when we do this, we're looking for changes in activation energy. So the questioning you're going to see is going to involve activation energy when ARRHENIUS is necessary. And the reaction that this is referencing here is this reaction below. There's our slope is equal to the negative of activation energy divided by R, and that allows us to calculate activation energy given some rate constant and temperature data. So here's that equation rewritten, where this frequency factor value we're going to have, we'll talk about that as we come to it in practice. But we have natural log of our rate constant, 8.314 for our Kelvin temperature and activation energy are our pieces of this big idea, and then that leads us to the actual ARRHENIUS equation here. This is probably what you'll use more than anything else in ARRHENIUS. So this is the variation. We have natural log of the rate constant at temperature 1, rate constant temperature 2 is equal to the activation energy divided by R. And then we have this expression where we have the inverse of temperature 2 minus temperature 1, or final minus initial. That'll help us be able to calculate any piece within this. So the rate constant is a first order reaction. The rate constant of a first order reaction is this value. What's the rate constant at 350 Kelvin if the activation energy for the reaction is that value? So this is activation energy. Here would go in this position here. We have a temperature 298, temperature 1. We have temperature 350 here. And then we're looking for the change in the rate constant. So there we go. We plug and chug. And in doing so, we're able to calculate our K value, and this is what it would be. So our K value changes when temperature goes from 298 to 350 from 3.46 times 10 negative 2 to 7.02 10 to the negative 1. So that's pretty much how that gets used. Now, you can see that you're sort of shackled by several things in this question that drive you to doing a calculation involving this equation. So for the purposes of practice and what we're doing right now, I would write this equation down and be prepared to use it in class. I want to go back to the actual ARRHENIUS equation here. This is what this is. We won't use this directly, and if we do, we'll give you whatever frequency factor we might have. But by and large, the equation you're going to see use of is this, because you've got two sets of conditions where you may have a final temperature calculated, or perhaps, like we did in our practice question, a final rate constant. But just to kind of go back over that, keep in mind that the slope of the negative activation energy divided by R is this rate constant divided by the change in the inverse of temperature yields you a slope that can get you activation energy. Okay, so keep this equation in mind and keep this equation in mind. So moving on into catalysts, this is sort of the last little slide out of the unit. So catalysts are substances that speed up reaction without being consumed. They produce a new reaction pathway with lower activation energy. A catalyst lowers the activation energy for both forward and reverse reactions. So this is looking at the Boltzmann distribution of particles that have an energy sufficient to achieve reaction. When we add a catalyst, note that the Boltzmann distribution has changed. We just moved the goalposts. Okay, our activation energy at this point yielded these particles here being able to achieve activation energy. But when we add a catalyst, note the distribution is unchanged. We didn't change temperature. We just changed the presence of this object that lowers activation energy. So instead of looking at from, okay, we have a different shaped curve all of a sudden, we're looking at the goal activation energy is being moved back. So that allows many more particles to achieve activation energy at the same temperature. So let's look at an actual reaction coordinate containing a catalyst in the diagram. Our original reaction would have this activation energy, so you would expect a relatively slower rate. Whereas when a catalyst is added, in this case called an enzyme, we see the activation energy decrease. Nothing else changed. All right, your particles are still moving at the same speed. You've got the presence of this substance that does something to change the reactions in a way that lowers activation energy. And when it mentioned the forward and reverse reaction activation energy is lowered, what that means is this. Out pen here. When you look at the reaction from the forward end, it means in this direction. This is the forward reaction. We see our activation energy is this value here. If we look at through a different set of eyes, the reverse reaction would be an endothermic process, clearly. Our activation energy is going to be this value from here to here. Either way, it's been lowered, okay? Taking this peak out, has lowered activation energy at the forward and reverse reaction. So it does a lot to change the kinetics of the process, and it can also change other features of the process too. The last couple of slides, enzymes are biological catalysts. Catalysts can be plain chemicals like metals like platinum are great catalysts, but we also have many biological catalysts throughout our bodies, and every organic system is going to contain chemical catalysts that are created by the cells of the body in order to facilitate chemical reactions. I want to make mention of two types of inorganic catalysts. Inorganic means non-living, okay? So this is something that is used in industry in order to speed a process that is otherwise either unfavorable or requiring too much energy to start, too great of an activation energy. A homogeneous catalyst is present in the same phase as the thing it's reacting with. So liquid and liquid, adding a liquid to another liquid to facilitate a reaction is a homogeneous catalyst. A heterogeneous catalyst exists in a different phase, and this usually involves a gaseous reactants being absorbed onto the surface of a solid catalyst, such as a car's catalytic converter. And this is what I was getting at, platinum. Certain metals have properties that allow them to act as catalysts, and platinum is one of them. The word adsorbs means sticks to. Absorption involves penetration into the actual surface. So adsorption means stick to, and absorption is penetration into. So this image you see here is a heterogeneous catalyst of hydrogenation of ethylene. And ethylene is a gas, and if you want to turn ethylene into ethane, this is the process. Isn't that neato? This is ethylene. This is a metal catalyst surface. This is free hydrogen in the system, and you're able to see this ethylene bind to the chemical catalyst, this metal in this case, and then facilitate the reaction of hydrogen atoms with that ethylene to turn it back into ethane. Totally awesome. And for fun, car parts. You know, most of you guys have driven a car. This is an internal combustion engine. This is not an electric engine. This is not a Tesla. But an internal combustion engine's engine waste in the form of carbon parts, carbon monoxide, carbon dioxide, exhaust gases are forced through what's called a catalytic converter, which contains a series of reactions designed to allow things to exit the car that are environmentally favorable. Nitrogen monoxide and carbon monoxide are terrible chemical pollutants. Carbon monoxide is a greenhouse gas, but it's much more favorable than carbon monoxide. Nitrogen gas is obviously part of the air and not at all any sort of a greenhouse gas. So more favorable emissions are allowed to be exited from a car because of the chemical reactions that take place inside the catalytic converter containing solid heterogeneous catalysts that are designed to make your exhaust fumes more environmentally tolerable. I appreciate you listening to this long-winded lecture. This is the final video for Kinetics. I hope you've taken high-quality notes. I'm sure there will be questions. Please bring them to class, and we will get them sorted out.